Okay, so let's have a look at it. Consider a random experiment of rolling die. Sample space is the set of all the possible outcomes. So if we roll a die, my sample space is equal 1, 2, 3, 4, 5, 6. Okay, an event is a subset of that. So it might be even numbers, odd numbers, prime numbers, whatever. Okay, so if A is the event of rolling an even number, from the sample space 2, 4, and 6 are the only evens. The event of rolling a number less than 4, 1, 2, 3, less than 4, so it's just 1, 2, 3. Now the intersection of those things that occur in both sets. All right, so let's go down to example 2 and we'll just fill it in as we go. So what elements are in both A and B and the number 2? So that's equal to A intersection B. The union is a combination of all the possibilities in either A or B or both. So what's in A or B? So 1, 2, 3, 4, and 6 are all the possible numbers. Now 2 is in both of them, but we don't write it twice. So we can say A union B. A dashed is the complement. That's everything that's not in A. So what's not in A? A is the numbers 2, 4, and 6, which are the evens. So 1, 3, 5 are all the numbers not in A. Okay, so that's just listing the events in each of the different sets. A probability then is really just the number of elements in the set that we want over the total possible number, over the number of elements in the universal set. So having looked at what we've just had a go at, so given that the number of elements in the universal set is equal to 6, the probability of A, well, what is A? A is up here somewhere. A is a 2, 4, or 6. So 3 out of 6, which is a half. The probability of B is also 3 out of 6. A intersection B. So there's only one element in A intersection B. So 1 out of 6. The union, there were 5 different elements. So we have 5 out of 6 for the union. Okay, so just, I think, relatively straightforward. All right, so different things that we need to just make sure we're aware of. No probability can be outside the range of 0 to 1. So a probability of 0 means something can't happen. A probability of 1 means something must happen, okay? If you add up all the probabilities for a particular outcome, they have to add to 1, all right? Probability of the null of the empty set is 0, all right? So we use that, we use the null set symbol, okay? Because if I say the probability of 0, it might mean the probability of 0 occurring, yeah? And if we have a dice that's got 0 on it, well, 0 can occur. So the null set is the empty set, 0 with a line through it, and the chance of it occurring is 0. The complement of A, the probability of it occurring is 1 minus the probability that it does occur. So the probability of A not happening is 1 minus the probability of A happening. And here's the first of our little rules of probability, the addition rule. So the probability of A union B is, so the probability of A or B happening is the probability of A plus the probability of B minus the intersection. And we minus the intersection so we don't count that value twice, all right? Now, another way to represent our probabilities is through use of a Venn diagram and or a Carnot map. So the Venn diagram, okay, is typically set A, we'll go set B, okay? And so what we can do is A intersection B, on my Venn diagram is that section that has both, okay? What have we got here? We've also got, what about the probability of A dashed intersection B? So things that aren't in A, but they are in B. So A dashed intersection B is this section. Yeah. What about things that are in A but not in B? So the things that are in A, all this area here, but not in B. Okay? And then finally, everything that's not in A and not in B is everything out here, isn't it? So let's just... So my Venn diagram or my Carnot map are really great as soon as we're looking for, if we come across terms with an A-B- intersection. Okay, so they're equivalent representations. So if we have a look, all right, so a new drug has some side effects. 8% of patients suffer only headache. So they get a headache but not nausea. So if you have a headache but not nausea, where's that going? Headache but not nausea. While 12% suffer only nausea. So they get sick but they don't get a headache. 75% of patients have no side effects at all. So that's no headache, no nausea. So we put that information in, then we can add everything up. 0.08 plus 0.75 is 0.83. This row here has to add to 1, so that's 0.17, which means up here, 0.05 plus 0.12 is 0.17. 0.12 plus 0.75 is 0.87. And 0.05 plus 0.08 is 0.13. Okay, so if we were to do a corresponding Venn diagram, just very quickly, nausea, headaches, what does it mean? So if you suffer from a headache and nausea, 0.05. If you suffer from nausea but not a headache, 0.12. If we suffer from a headache but no nausea, 0.08. So what does that mean? So all the people in nausea adds up to 0.17. All the people in headaches add up to 0.13. And then 0.75 would obviously be that section out here. Okay. What percentage suffer both side effects? So where's both side effects? You have a headache and nausea. So the final answer there is 5% of people. All right. They asked me for a percentage, so I gave them a percentage. Little definition number 1. Mutually exclusive events. If two events are mutually exclusive, it means there is zero intersection. So as soon as you're told that two events are mutually exclusive, we know that there's no intersection. Or if we discover through our course of our time that our two events have a zero intersection, again, it makes them mutually exclusive. Right, have a look.